going to be a quick video to explain how to work force problems that also involve acceleration problems. So for my problem that I have here, first thing I always need to do is to draw a picture. So it says that there's a car accelerating from rest. So I can draw a car, but let's assume you can't. If you can't, just draw a box. You could draw a circle. It really doesn't matter. So this box can represent my car, and it's accelerating from rest. And that means it's going to have an applied force that's acting on my car in order to move it. Another thing that I know about my car is if it's touching the ground, it has to have a gravitational force pulling down on it, but it also has to have a normal force that's pulling up on it so that it's not sinking through the ground. Something else that I know about this problem is that my normal force and my gravitational force, they basically have to cancel out because my car is not moving down through the ground. Let's let this be the ground. It's not moving down through the ground, and it's also not floating up into the air. My car is moving to some direction. The problem doesn't specify it, so I'm just going to draw my applied force to the right. If it's asking me to find the net force acting on the car, that means I have to work an F is equal to ma problem. If it's asking me to find the force, that means I need F. I don't know it. Now, I do know the car's mass. It tells me in the problem that the car has a mass of 1,100 kilograms. And then I need A in order to put it in here, but I don't have A. What I do happen to have is it says that it goes from rest to 60 kilometers per hour. So what that is a VI and a VF. From rest would be a VI of 0, and to 60 kilometers per hour would be a final velocity. The other thing that it tells me is that it has a distance, which is delta x, of 45 meters. Now, I know enough about physics at this point to recognize that I can actually find acceleration if I have these three things. It is possible for me to put those things together and to calculate it. The equation that's going to serve me best is VF squared is equal to VI squared plus 2A delta x. I have three of those four pieces. The only other thing that I'm going to have to recognize is that the units of speed, as I have them right now, are kilometers per hour. And I need to convert that to meters per second. We've talked about in class that if I divide by 3.6, I will get a speed of 16.6 repeating meters per second. Now I'm going to save all those digits. I've already done it. It's here in my calculator. And I'm going to keep that number. It's going to go here as my 16.6 repeating squared. VI is 0 plus 2 times A times 45. So since I've already got this number in my calculator, it's really easy to just simply square it. And then that's going to simplify on my paper to that plus 90A. So A will be equal to that number divided by 90. My acceleration is going to be 3.08 and a bunch of numbers meters per second squared. Now, if you're in my class, you know that we try to keep all of those numbers. I'm just not going to clear it out of my calculator yet. I'm just going to leave it there. That's going to go up here into my F is equal to ma problem. I now have acceleration. I now have mass. I'm ready to find force. My mass is 1,100 kilograms times this A number I just did, 3.08 meters per second squared. So the number is still in my calculator. Now I'm just going to multiply it by 1,100. And I will end up with 3,395 and some change. I can only have 2 sig figs. I had 2 sig figs here. I did have 3 out of my other original number over here. So 2 is the least, it's less. So that will be 3,400 newtons as my answer. Alright, I have one more problem that I can show you here. Right here. I have a 950 kilogram car in this particular instance, and I gave you some different information. So, again, here's my hypothetical car. It's traveling, so again, it has a force of gravity pulling down and a force of a normal force, a force of normal pulling up. It's traveling at a constant speed. And so it says that it's traveling, then there has to be some sort of applied force to make it travel. But this time it tells me that there's friction. And it says that there's actually F of F is 350 newtons acting against the car. Because I know that friction opposes motion. So it's going to be acting in the opposite direction. If you took these two things and flipped them this way, it would have no consequence on your problem. It'd be perfectly fine. Once again, those two things are going to cancel out because my car, I know if the road is here, the car is not going to be moving up and it's not going to be moving down through the ground like a sinkhole. It's going to have to be moving right and left based on my picture. Okay, when it tells me constant speed, one of the most important things here is that constant speed or constant velocity, in my mind, always needs to equal 0 meters per second squared for acceleration. That means my car is not accelerating. 0 acceleration does not equal no movement. What it also means to me is that the applied force has to be equal to the frictional force. If the applied force was greater, then it would be accelerating. It would have a net force. In this particular case, there's really no math to be done. It's just me knowing that the F applied has to be equal to the F of F in order to have 0 acceleration. So F applied is also 350 newtons. So to do a little bit more math, we have one more problem. We have a very bored physics teacher with a brick. So a brick's pretty easy to draw. So here's our brick, and it's attached to a string. And it says that it is a 4-kilogram brick, and the person is pulling up on it. So what that means to me is this string is actually going to have a tension force on it because it's a hanging object. In this case, it's not a normal force because it's not sitting on a surface. And I know that there's also going to be an FG that's pulling down on the brick. Okay, it says that the brick accelerates upwards. So I know that A up here is 3.2 meters per second squared, and I know that the brick weighs, it has a mass of 4.0 kilograms. And it wants to know how much force did the teacher use on the brick. Okay, well, first thing first, if I have a problem where I have a brick, I'll draw it down here. If I have a brick and I have an FG, I'm going to make up some number. If the FG is 10 newtons, and a person is pulling up with 10 newtons, then that brick isn't accelerating. It's like the problem that we just did here. If the two things are equal to each other and it's moving left to right, then there's no acceleration. But this problem tells me it is accelerating, which means to me that in the end of things that Ft has to be greater than Fg. So if I have this brick right here with 4 kilograms and I have this acceleration, it's pretty simple for me to just simply put it into a problem here and go F is equal to ma. My mass is 4.0 kilograms. And then what I can simply do is go from there and calculate the rest of my problems. Okay, in this particular situation, here's the deal. If we just said that the two have to be equal right here, if you pull up on this to just simply oppose gravity, you would be pulling up with a tension force that's equal to the Fg. If I calculate Fg for a second, I know that down here, gravity is accelerating my brick at 9.8 meters per second squared. So I know that the force of gravity on this particular brick is going to be 4 kilograms times 9.8 meters per second squared. That's equal to 39.2 newtons. So what I'm telling you is if I just simply pull up with 39.2 newtons on the brick, it's not going to be accelerating. So that means that the person also has to be pulling up 39.2 newtons on the brick, plus whatever force they're putting on it to pull it up. So if I take my 4 kilograms and I multiply it by 3.2 meters per second squared, that gives me a force of 12.8 newtons. So there's kind of two forces going on at the same time. I have to be pulling up with 39.2 newtons, but I also have to be pulling up with 12.8 newtons in addition to that. So I have a tension force and I have an applied force. And how I've got it written, now that I put the words in there, don't do me justice. So the tension force on it is 39.2 just to oppose it. And then I have an applied force of 12.8 newtons in order to get it to move with an acceleration that's greater than 0. So in order for me to figure out my total force that's on the brick, I'm going to have to add the two things together. I'm going to have to take my 39.2 and I'm going to have to add it to the 12.8 in order to get a total force, and that's going to give me a total force of 52 newtons. And if I go back to my sig figs, it's perfectly acceptable for me to have 2 sig figs on this. So that's going to be my final answer.